we're going to discuss Gauss's law along with some examples of it. So Gauss's law was discovered by this guy right here, Carl Friedrich Gauss. And what Gauss's law said, he said that the flux, and if you'll remember, the flux phi E, which equals the electric field passing through a certain area, or an area, is proportional to the charge enclosed over epsilon naught, this charge constant. So if we draw some field lines, that's a positive charge, so the field lines are going to go out, because field lines point positive and negative. If you draw a circle around this, or a sphere, because charge lines are going to go here, in spherical, radial symmetry, of some area vector, and again, if we draw area vector, remember the area vector points perpendicular, so you're looking at things going perpendicular to this. The flux through that surface will be exactly the same as the flux through this surface. So phi for the big surface will equal phi for the interior. So let's kind of get a brief understanding of what this is. So if we're looking at this, and you've got some electric field permeating space right here, you've got some, I'm just going to make a rectangle right here. So on this side, this would be dA. On this side, this is dA. So if you look at the flux, I'm going to call this side 1, call this side 2. If the flux, this would be the flux through side 1 plus flux through side 2. Sides 3 and 4, there's no field line coming through there, so this is 0, 0. If I add these together, this would be equal to flux on side 1, same direction, cosine of 0 is 1, so this would be 3a plus cosine 2. In this case, theta would equal 180 degrees. Therefore, this would be negative 3a. So your total flux is 0. And you can see this because if something's coming in, something's coming out. So let's move this and do a real quick example. One where theta is not equal to 0. Say you've got a plane right over here, and this would be your dA. This would be your electric field. This would be theta. So in here, your flux equals whatever E is times this area times the cosine of theta. Pretty much all this is saying, all this theta right here, all it means is how effective is this surface at getting flux out, or how much of the flux is in the direction pointing out of your shape. So Gauss's law, you just count the field lines coming through a surface, and it's going to be constant, because like we said, electric field proportional to 1 over r squared, and then area is proportional to r squared. So let's talk about how to use this right here. First thing, you'll notice I wrote Q enclosed. That's because if you have some weird surface here, and there is a plus charge, the field lines from this are going to go out. But if you have this charge outside, I'll make this another plus charge, the field lines from it go in, so negative flux, and out, positive flux. Therefore, the only charge that matters is the charge enclosed. So let's look at something else real quick. If we examine this, why does it work? Why is this a constant? So E is K, which we're going to write K as 1 over 4 pi epsilon naught, permittivity of free space, which is pretty well how well an electric field goes through the vacuum. So if we're looking at this, we write out the electric field, write out the area of a sphere, 4 pi cancels, r squareds cancel, and you're left with just this Q enclosed over epsilon naught, because the electric field is proportional to 1 over r squared, and then area increases as r squared. So the growth in the area cancels out the fallout of the electric field. So where Gauss's law really shines is when you start looking at these symmetries. All right? Because when it's symmetries, that little area vector is really easy to figure out. So we're going to start with a sphere, then we'll talk about a cylinder, and then we'll talk about a plane. So starting to look at a sphere, if you have a charge, right, and you want to find the electric field here. Well, you know that the electric field from a plus charge goes out in all directions, and it's in 3D. So a Gaussian surface running through this point would be a sphere. All right? And this sphere would have a radius r, which would be the radius of the circle. So if we're using Gauss's law, let's start with writing this. So the total flux equals E integral, I'm just going to do this, integral dA, E dot dA equals Q enclosed over epsilon naught. Well, E is a constant, because it's going out in all directions, which is what we have to use. We have to use that E is a constant. E is a constant. A is going to be the area of a sphere. You integrate a little chunk of the sphere over all the sphere, so you get 4 pi r squared. And this is going to equal Q enclosed over epsilon naught. So if you solve for E, you get, by the way, this only solves for the magnitude. You have to apply the direction yourself. So E equals Q over 4 pi epsilon naught r squared. And if you remember 4 pi epsilon naught, or 1 over 4 pi epsilon naught, this says that E equals KQ over r squared, which is exactly what we got before. And the final piece of this is that you know that your electric field is a vector, so you have to look at this. Which way are these pointing? Well, they're pointing radially outward, which is our hat. So let's say that you have an infinitely long wire with a charge density lambda. Now, this wire is infinitely long, so it's just going to keep on going forever, up and down. But if you'll notice, since it is infinitely long, if you have a field line going like this, you'll have another spot somewhere around, and since it's infinitely long, you'll have infinite of them, that comes here. And what do you know? This angle equals this angle. So the only electric field that you're going to be left with is something that points this way, or this way, pretty much all the way around, but straight out. And I'm going to call this S hat. S hat, just a funny way of saying it's going around in a circle and splitting out. So what you need to do, you need to draw a Gaussian surface. Gaussian surfaces are these little shapes that we draw around here. In the last example, it was a sphere. Since this is a cylindrical symmetry, I'm going to draw a cylinder. Makes sense. So let's look at dA. On the side, it points this way. On the top, points this way. And on the bottom, points this way. Now this linear charge density is important because you don't know what your total charge is, because the wire is infinite. Hard to measure infinity. But you can tell for a small chunk what its charge density is. And if we know, we can get the total charge enclosed in this Gaussian surface is equal to lambda L. Okay. So let's take a look at this. Start with Gauss's law. Flux equals integral E dot dA. In this case, E is constant, and this is Q enclosed over epsilon naught. So let's plug this expression in here. Lambda times some arbitrary length over epsilon naught is equal to your electric field, E dot dA side plus E dot dA top. I'm going to have to write this plus E dot dA. Again, all these integrals, dA bottom. Take a look at your components. There is no part of this electric field that's coming straight out of this wire that goes down, which means This is 0. That's 0. So all you're left with is that E times the area of the side. In this case, it would be 4 pi s, that's the circle around it, times L equals lambda L over epsilon naught. So this right here is the distance around, that's the circumference of the cylinder. L would be this length. Draw that in here. This is L. And this would be S. We'll notice that these L's go away, and you are left with E for a cylinder, infinitely long cylinder, equals lambda over 4 pi, how far you are away, epsilon naught, radially outward from the cylinder. One more example. Final example is a plane. So when you have an infinite plane, alright, here's our infinite plane. They call this a Gaussian pillbox. And just like before, the only directions that you're going to run with flux are up and down. Because if you're over here, you've got a component going this way. Over here, you've got a component going this way. So the only net result is that your electric field points straight up and straight down. It's not going to go through the sides at all. So using Gauss's law, you get the flux equals integral E dot dA. In this case, the only sides that are going to matter are the top and the bottom. Now keep in mind, even the bottom is negative. This is dA for the bottom. This is dA for the top equals Q over epsilon naught. So you get E. Let's make this, we'll call this area of this box, we'll call this area A. So it's EA plus EA equals Q over epsilon naught. We don't know total charge Q, but sometimes what you do know is a charge density. So this sigma would be coulombs per meter squared. It's an area charge density. So I'm going to move this whole thing up real quick. Just like this, so we can fit our last line in. Plugging this in, you get 2 EA equals sigma A over epsilon naught. Your A's cancel, and you get E equals sigma over 2 epsilon naught. In this case, on top of the plane, it is plus or minus z hat. And I'll just call this the z hat direction, away from the plane. The neatest part about this planar example is that it winds up being a constant. No dependence on length, no dependence on L. The electric field from a plane, no matter how far you are away, stays the exact same. Well, I hope that helps. I know this video was a little bit longer, but hopefully it'll clarify some things with Gauss's law. I'll see you in class.